So yesterday we dealt with a couple of important processes for energy losses. Okay, remember what we said: E plus gamma upscattered in E plus gamma prime. Of course, I got a question afterwards: why inverse Compton? What about Compton? Of course, you can read these as a scattering of the photon onto the electron, and that's the Compton process. And historically, that was the first one to be studied in the lab. It's just that this process is not that much important in cosmology and astrophysics, and this is a useful exercise to do. People get often confused, although the cross-section, right, is the same. It's the same process. The mean free path, or if you wish, the interaction rate, depends on the target density. Okay. Remember, the mean free path was 1 over n sigma. So even if the sigma is the same for photons and electrons, for a photon, n here is the electron density. For an electron, n here is the photon density for this process. And in the cosmological environment, there are at least 400 photons per centimeter cube of the CMB, but the electrons are some 9 orders of magnitude below. So a photon, unless it can interact with other photons, do pair production, well, a photon is basically free to propagate, although an electron will see lots of photons around, so it will do inverse Compton. Okay? That's why I discussed the inverse Compton and not the Compton process, because practically that's what matters. Okay? Apart from this parenthesis, well, the other process that we discussed was the synchrotron radiation, synchrotron losses, so where this happens in a pre-assigned magnetic field. Today I will discuss some interactions, later on, some interaction of hadrons with radiation, but before that, let's focus on lepton first and hadron interaction with matter. Okay? These are generically called ionization and Coulomb losses. And these are exactly the interactions that are important at low energies. If you want to compute the spectra of cosmic rays in the range, in the energy range measured by Voyager, say tens of MeV or so, well, you should worry about this. Okay? Now, imagine that you have an electron propagating into a medium. Could be a gas. This happens also on Earth, on an electron propagating in a target in a metal or so, with some density of electron E, and passing at some distance impact parameter B from this electron. What happens is that this has some velocity v. Okay, let's start with a non-relativistic case, and then I will justify why this is still valid in the relativistic case. Well, this is a high-energy electron. It will transfer impulsively some kick to the electron in the target material. Okay, so in this transfer, this one loses energy. The material gets some thermal energy at the end. And this continuous loss may lead to significant alteration of the energy spectra, for instance, of this electron. Now, what is the typical range, or if you wish, the dE over dx of this process? How fast this particle loses energy while crossing a medium of density Ne? Okay, first thing first. On dimensional ground, can we estimate what's going on? The answer is obviously yes, apart from some numerical factors. On dimensional ground, clearly, this process must be proportional to the typical cross-section with which this electron interacts, a Thomson cross-section. The number density of your target. Yes? B. It's the minimum distance from the target under consideration. Of course, there will be a distribution of B So we will see what happens once I integrate over all possible b's, okay? Sorry if it's not clear. And then there is an energy scale. The only energy scale is the mass of the electron, or in general, some energy of the electron. Okay? Or the velocity, if you wish. So the final result that we'll get should look something like that, okay, on dimensional ground. We'll see that this is the case. What's the type of interaction? Of course, it's electromagnetic. It's an electric interaction. What's the kind of change in momentum imparted to the target electron? Well, that's Newton's law. So this will be given by the impulsive force times the time of the passage. I will just do an order of magnitude estimate here, not the exact calculation. I will tell you what the more exact calculation will give you. And probably you have seen this exercise done before in elementary courses. Okay? So what's the typical time scale of the passage of this particle near the electron for an impact parameter B? Well, of course, this delta B will be of the order of B over V. And then you have the force, which is electrostatic. So it's going to be E squared over B squared. So we combine these two. The transferred momentum will be F times delta T. So it's going to be E squared over B times V at the denominator. And then what's the transferred energy? Delta E, non-relativistic approximation. So this is going to be of the order of delta P squared over ME. I'm forgetting factors 2 here. Huh? Don't take these literally. So the delta E will be given by e to the 4th over B square V square ME. And this is for a single encounter at an impact parameter B. Of course, now there will be a distribution of impact parameters. So I have to integrate, in order to have the range, I have to integrate of all possibilities. So my minus dE over dx, it's a negative thing. I'm losing energy. That's why I write the minus here. It's going to be, this is a 2D slice. You should imagine this as a circle with impact parameter between B and B plus dB. And now I integrate over all possibilities. So this is dB 2 pi B, the number of targets, and E, and then the delta E corresponding to the single energy transferred at a given impact parameter B. And you see that dimensionally it's fine. This is an energy. This is 1 over length cube, length square. So we are fine. What's the result of this integral? 2 pi. Then you have a B that goes away with this B square. So you get some log of B max over B min. Then there is e to the 4th over V square. E to the 4th over V square. Then I multiply and divide by M. M is square times ME. And then there is an NE. Okay? So forgetting about factors of order 2, these and these is basically sigma Thomson, number density, mass of the electron, the only scale in the problem. And then there is this logarithm of B max over B min. What is this? Well, this is the so-called Coulomb logarithm. Okay? The electrostatic interaction is 1 over r squared, so there is some specificity of that. If you are very far away, basically you don't see anymore the charge. This is, if you wish, related in a plasma to this Debye length that was discussed. And then there is some cutoff related to the fact that low velocity, what happens is that at the low velocity, this treatment is not valid anymore because it's not true anymore that this is a sort of small quantity, a little kick, but you have a hard scattering. It's like in Rutherford. Yes? Yes? Yes, that's what I'm saying. So these are the extreme of integration. Okay? Which I'm justifying physically what they correspond to. Okay? Of course, I cannot integrate. I can formally integrate B to infinity, but that would be inexact because it's not true anymore that if this guy is infinitely far away from my charge, it sees anything, right? Because of this shielding. So if it's very far away, the electron doesn't see a charge, and so there is no transfer. Okay? So this cutoff, it's a cutoff at large distance that corresponds to the screening length of my system. Okay? The distance beyond which I don't see the charge anymore. And this B min has to do with a number of things, but you can think of as the limiting factor in which the approximation breaks down, because now I'm assuming that this is receiving a little kick, there is a small fraction of this energy transferred, et cetera, et cetera. It's not true anymore. If you have a very, very close encounter, this will be a very energetic process, and that's why this treatment fails. Okay? So this is just a number anyway in this approximation. But we recover basically the, well, there is a V square that I forgot, which is very important. And this is closely related to a formula that I'm sure almost all of you have seen, which is the Bethe energy loss formula. And that describes how a charged particle loses energy in a medium. Experimental physics, you must have seen this several times. Of course, it's not the complete formula. A more exact treatment takes into account quantum effects and would lead to a result which I just write down here. And E divided V squared, you see we refine the same factor. And then there is a constant, which a numerical constant, I don't write it down, plus logarithm of E over ME. And then there is some correction that depends on beta square, etc. This takes into account the quantum mechanical nature of the process. Here it's pure classical treatment. And, okay, it takes into account a little bit more subtleties, but you see that apart from this logarithmic dependence over upon energy, we get basically the same result. Now, if you plug in numbers, this is not a ridiculously large energy loss for the densities typical of the medium, of the interstellar medium, okay? What's the difference with respect to the lab where this is a very important formula? It's basically here. The densities are very, very low, okay? One thing that justifies the fact that this is roughly valid also in the relativistic case is the fact that in the relativistic case, what I computed this transfer delta P, when I computed it, I assumed this impulsive transfer force times delta T. But now in a relativistic case, what will happen is that one is augmented by factor gamma, the other is reduced by factor gamma. So at the end of the day, you get the same result. Okay? So one can argue that this is still valid when the electron is relativistic. There are other effects. For instance, at some point, radiation emission will start to matter. I will mention it in a second. But roughly speaking, you can use this formula for estimates. Of course, these constants here, or this hidden factor here, will depend on the state of the gas or the plasma or whatever else, the solid in which I'm going through. Okay? So I'm hiding the dependence on the material in these things. Sorry, these or this one here. And typically, these are tabulated, okay? If you go to the particle data book, etc., you ask what's the value in hydrogen, etc., you find the empirical coefficients that are related to the binding energies and things like that. Yes? No, this is an electron. Or in principle, actually, you could repeat exactly the same argument also for protons or for nuclei. Okay, this is just a gas, if you will, or a plasma. Huh? It's exactly the same thing, or it could be a solid, actually. There is no solid in astrophysics, but the calculation is exactly the same. Of course, I'm considering electrons for the simple reason that these are the ones that have way less inertia than protons, so these are the ones that are kicked out of your system much more easily. This is always true, right? If you go with a high energy particle through a medium, the ones that suffer mostly the recoils are the electrons, not the nuclei. Okay, there will be, of course, some interaction with the nuclei. Okay, so this is not particularly important at very high energies, but as I said, when you go at sub-GeV energies or so, these are the dominant energy losses, so you should take into account. Of course, you can also apply them to nuclei. The only difference is that there is a factor z square that enters because now in this interaction, in this force here, the force will be given not by that, but there will be a factor z square. Yes. If z square, etc., there will be a z1, z2. Let's put it this way. Z1, Z2, if you have charges different from the electronic one, okay? However, you see that the fractional energy loss for nuclei will be lower. Why? Because nuclei have a rest mass which is much, much larger than the one of electrons. So at a given velocity, the range, the energy loss per unit length is the same if z is equal 1. But at a given velocity, a nucleus carries much more energy than an electron, okay? What else I wanted to say? Yes, of course, now you can go a little bit further. What happens if now I start having analogous of this process in the sense that you have some electron hitting on this medium that I write abstractly, like that, and it radiates a photon. This process is called Bremsstrahlung, okay? And it's a stopping radiation, if you wish. I won't do the calculation in detail for two reasons. One is that it's very long in general. The second reason is that we are not interested that much in this process. It's not the most interesting process for applications in high-energy cosmic rays. I want to mention a few features of this process. The first one is that, okay, you can write down some schematic diagram, okay? This is our electron. This is, in general, a nucleus, okay? These might interact through a, okay, let's write it this way, okay? Okay? This is a typical diagram associated to the emission of your breaking photon. Now, there are a few considerations that you can make to estimate what's the cross-section associated to this process. Okay? How many vertices? There are 3. Huh? So here there is a charge E, there is a charge E, there is a charge Z times E. So in terms of amplitude, this is something like Z times E cubed. And then there is the propagator of the electron here, ME. You square this in order to get a cross-section starting from the amplitude, and you will end up with Z square. This is you see e to the 6, so this is alpha cube, which means you can rewrite this alpha times the sigma Thomson, because there will be an alpha square, an alpha square or a q to the 4th over mass square. So this is equivalent to saying that the sigma Bremsstrahlung is suppressed by factor alpha with respect to the Thomson cross-section. Could be enhanced if you have heavy ions as target. But numerically speaking, this is suppressed with respect to Thomson. And another important feature that I just state is that in the range, or if you wish, in the energy loss rate, minus dE over dt, basically this is going like sigma Bremsstrahlung times the target of electrons times energy. So it's linear in energy. Okay? So if you have, in general, ionization and Coulomb losses, and then you have Bremsstrahlung, it's clear that these will kick in at higher energies than the other one, because that one is like sigma Thomson, but no energy dependence, or a very weak logarithmic energy dependence. This has a prefactor which is more than 2 orders of magnitude lower, but it grows with energy. So typically, a regime where electrons, in the interstellar medium, where electrons lose energy dominantly, cosmic ray electrons lose energy dominantly via Bremsstrahlung, is a few GeV, like 5 GeV, something like that. One thing about applications of this is a very, very crucial process in the nice X-ray images that you might see of clusters of galaxies. Okay? This is basically the physical process through which the electrons in clusters of galaxies emit X-rays that are detected by X-ray telescopes and that are used to do whatever, like mapping the dark matter distribution. And I don't know if you have seen the bullet cluster with this segregation effect between the wet cleansing reconstruction of the mass and the X-ray reconstruction of the baryons, the baryonic gas that is shocked. Well, that image, those photons come from this process. Okay? It's cosmology, it's not high energy cosmic rays, but I want to mention where it comes from. Okay? Let's move on to hadronic interactions, because these are very, very important as well. I can start using that one for a few generalities, maybe, before moving to hadronia. First of all, nuclei, protons, or helium nuclei, hydrogen nuclei, etc., these are charged particles, okay? So in principle, I can repeat what I said yesterday for synchrotron or for inverse Compton for these particles as well. Now, why people tend not to discuss this in the first place? Well, the secret, so to speak, has to do with the scaling of the different scaling that this process would have with respect to the electron case. Okay? So if you remember the sigma Thomson, this is 8 pi or third alpha. Let's write directly like alpha square over me square. This was computed for the electron yesterday, if I didn't do any mistake in the numbers. But now for a nucleus, what happens? For a nucleus which has charge z times the electron 1, of course there will be, with respect to sigma Thomson, there will be a factor z square here. There will be z to the 4th, because it's alpha square, so it's z to the 4th. And then there is a factor a square times the ratio of what? Of the mass of the electron over the mass of the nucleon squared. Okay? So basically for a nucleus, this thing here is roughly 3 × 10⁻⁷. So you go from a fraction of a barn to something which is basically below the microbarn. Okay? And so there are many more important processes for hadronically interacting, so strongly interacting particles than these ones, and that's why you don't typically hear about those. Although there are situations like the extreme ones discussed by Kota yesterday, where there might be a contribution of proton synchrotron, for instance, okay? But usually these are way, way suppressed with respect to other things that I'm going to mention. This is just a parenthesis. Huh? So what about nuclear reactions, okay, hadronic interactions? We know that the theory describing this is QCD, quantum chromodynamics. This theory confines, which means that at sufficiently low energies, basically the degrees of freedom of your theory are not anymore the gluons and the quarks. The particles are hadrons and nuclei in particular, and effectively they interact through these pions of the nuclear interactions, okay? And this is a strongly coupled theory, even the effective theory at low energy, or if you wish, the coupling, the nuclear coupling between the pions and the nucleons is of order 1, okay? So there are two ways to see this. Either you write a theory of pions and nucleons and you play with that, but the perturbative approximation is doubtful. So there are very, very large non-perturbative corrections. Or you just can estimate a few things phenomenologically and then use the data just to calibrate this theory, okay? So let's follow this second path, but the two things give comparable results, of course. So from the point of view of macroscopic observer, a proton or a nucleus is not a point-light particle because of this effect. So its constituents are partons, quarks, and a gluon Z. And it acquires, as a result, a finite size. And this finite size is roughly 1.2 Fermi, which is 10 to the minus 15 meters, times a to the 1/3, roughly. A is the number of nucleons in the nucleus, okay? Just because of this fact, this size, by the way, is related to the QCD, to the confined phase of the QCD. This has to do with the scale at which your theory becomes non-perturbative. Huh? But geometrically, this is associated to some cross-section pi r square. And if you plug in numbers, this will give you something like 45 millibarn times a to the 2/3. Roughly. Huh? If you look at empirical data of what are the typical inelastic cross-section among nuclei, well, this reproduces quite well the values that you find. So without knowing anything about quarks, gluons, and etc., just encoding this information here, we get the right order of magnitude of the cross-section, okay? Notice these are very, very large compared to those scales I was talking before, sub-micro barn. So basically, that's why you can forget about this quite often. That's the first thing. The second thing I wanted to mention is that, okay, if you move at the energies that are of interest for us, which are typically GeV or above, these are comparable to the Compton wavelength of your nucleons in the nucleus, okay? So although at low energy, the interactions between nucleons and nuclei are very complicated. That's the realm of nuclear physics. And the typical energies of these processes are MeV, few MeV. Once you are in the GeV range, it makes sort of sense that your particle, imagine a proton that hits a nucleus of carbon in the interstellar medium. Basically, these will resolve this carbon as the sum of n nucleons. So typically what happens, it interacts with one nucleon among these, or maybe two. So you can describe this as a superposition model. This is related to the fact that the energy of cosmic rays is sufficiently high to resolve the nucleonic nature of your nucleus. And if this is the case, okay, what happens if you have now a collection of balls, and your particle enters, kicks this one out, bounces back, and then this remains more or less unchanged. So effectively, what happens is that in these processes, the energy per nucleon remains roughly constant. Okay? And this is a property that even Pasquale mentioned when discussing the boron over carbon phenomenology and all that. This process where the nucleus loses one or a few nucleons at best in a typical collision at GeV energy is called spallation. Okay? And that's responsible for instance, for transforming when a proton hits a carbon-12, transforming it into some boron-11 plus proton, and similar processes. Okay? What are the typical cross-section of these processes? Well, if this is the scale of the overall cross-section, not surprisingly, these cross-sections are a factor of a few below this. So I give, in the notes, I report a table taken from Longair about typical values of cross-section for, I don't know, a carbon-12 to spallate into a boron-11 or boron-10, etc. And you would notice some patterns. Typically, the largest cross-sections turn out to be the partial cross-section, turn out to be the ones where this nucleus, be it target or projectile, loses one nucleon. Sometimes two, something like that, related to the stability maybe of the daughter nucleus, etc., etc. But typically, this is the dominant effect. So although in principle, this is a very complicated problem, right? Because if I start with a cosmic ray nucleus of iron, and now I say, let it propagate in the galaxy, of course, every time it collides, it might lose 1, 2, 3, 4, 15 nucleons. I should keep track of all these branching ratio, etc. This is done sometimes in calculations, etc. But to leading order, you can think of it like a sequential loss of one nucleon at a time, and this has some simplification. Okay? One more thing. Not always the daughter nucleus is stable. Sometimes it's unstable. So on one hand, this is related to these cosmic clocks that Pasquale was mentioning about, because if the lifetime is very, very long, well, you might use some of these as a measurement of the confinement time of cosmic rays in the galaxy. But there is another consequence of that, which is, unfortunately, as far as I'm concerned, very poorly explored empirically, observationally, which is that some of these nuclei are unstable via gamma de-excitation. Okay? Some of these nuclei are created in an excited nuclear state. They de-excite, they emit a gamma ray, whose typical energy are, say, of order few MeV, of course, 10 MeV or so at most, because that's the typical nuclear energies. You might have lines, gamma ray lines, associated to these processes, which could tell, in principle, a lot about what's going on in the interstellar medium from the collisional point of view in the hadronic sector. But till now, as far as I know, there is very, very poor counterpart, observational counterpart on that. So if you are interested in observational astrophysics, and you have a clever idea, which is not too expensive, that's one sector which is almost unexplored. Okay? So far, so good. We have limited till now to relatively low energies. So if you want to know, basically these kind of processes are especially important up to, maybe tens of GeV. Of course, they go on even further, but they won't be anymore the dominant processes to lose energy once other channels gets open, and I will mention now what happens. In particular, these are completely relevant for stuff that propagates over extragalactic distances. Okay? Why? Because you need target. Okay? You need some nuclear target to hit. the density in the galaxy is already of the order of 1 particle per centimeter cube. If you go to the extragalactic space, this drops to below 10 to the minus 6. So forget about, these are very, very important for galactic cosmic rays. For ultra-energy cosmic rays, basically you forget about them, okay? So what do you care about for ultra-energy cosmic rays? You care about a few processes that you have heard about. These related to the GZK cutoff, the Bethe-Heitler process, photopion production related to the GZK cutoff. Before that, there is an even simpler effect in energy loss, which concerns particles propagating over cosmological distances. I think Pasquale mentioned that. What happens if you have an ultra-relativistic particle? This particle is associated to it behaves like radiation, right? What happens to radiation in an expanding universe? Its wavelength gets stretched. Okay, so there is a simple phenomenon, which is that as the universe expands, and the rate of expansion of the universe is the Hubble function, which is nothing by the a dot over the time derivative of the scale function over the scale function. As a consequence of this, the wavelength of all these particles, relativistic particles propagating over cosmological time scales, gets stretched. So this particle lose energy adiabatically because of that. So there is a simple energy loss term, 1 over E dE over dt, which is nothing but the Hubble expansion. Or more conventionally, you can write this as a function of redshift, and this is typically for all situations of practical interest, 1 plus z cube omega m plus omega lambda, or if you wish, 1 omega m in a k equals 0 universe, okay? Flat case. This is not extremely important, but it's there, and it affects all relativistic particles propagating over extragalactic distances. Okay? Of course, what's the typical scale over which a particle loses a significant fraction of its energy? Well, the Hubble time or the Hubble distance, by definition, right? Not very difficult to understand. If you have enough energy, however, to say a proton has enough energy that on basically the only or almost only target of relevance, which is the CMB for particles propagating in the extragalactic sky, can produce a pair, then this process becomes dominant with respect to that one. So on a more microscopic level, this process can be described, this is the proton, or in general, this can be a nucleus, because you have the analogous process for nuclei, of course. This is the photon of the CMB, and then you can have the plus C minus. This is known as Bethe-Heitler process. Okay. What is the threshold for this process to take place onto the CMB? What's the energy at which protons, for instance, start opening up this channel? Okay? The formula I discussed yesterday for the center of mass square energy kicks in again. So you write just S initial equal S final at threshold, and you derive the energy at which this process starts to be open. Okay? This equation leads to m proton square plus twice E proton epsilon of the CMB, 1 minus cosinus theta equal m proton plus 2me squared, because this is a threshold, so there is only the rest mass energy here. And as a result, at threshold, when this is maximized, you get the E proton must be larger than m proton times m electron over the energy of CMB photon. And if you plug numbers, this gives you roughly 2 times 10 to the 18 electron volt. So for protons which are above these, of course you can repeat this for nuclei, yeah? And you get similar numbers. For protons which are above this energy, they see the photons of the CMB energetic enough that they can be converted into a pair in the field of the proton. Okay? This process, however, from the energetic point of view, is not extremely efficient. Okay? At threshold in particular, you can think of it like a compound state decaying into a proton, a daughter proton plus 2 electron positrons. So roughly the inelasticity, so the energy lost, is going to be of the order of twice the electron mass over the proton mass. And this number is 10 to the minus 3. So every time such an interaction takes place, roughly, if it's not too far away from threshold, your proton has lost 0.1% of its energy. So basically, this is almost a continuous energy loss process, first. And second, again, look at the diagram here. 3 vertices. There might be here a Z if there is a nucleus. But basically, this is, we can repeat the same argument as before. The cross-section for the Bethe-Heitler, not 6, the cross-section for the Bethe-Heitler process is going to scale as alpha cube me square. This is very similar to what we did for Bremsstrahlung, times Z square if there is a nucleus, not the proton, times a numerical function of the energy and the charge, which is of order 1, let's say, for our approximation. Again, this is not extremely large as a cross-section. So this process is both not extremely efficient and not extremely likely, although once it's open, of course, for protons that are propagating over gigaparsec distances, this becomes more important than the adiabatic losses. Okay? There is another consequence of this process, which I just mentioned. Of course, you might wonder what happens to these electron positrons in the final state. Now you should know the answer. If I inject these electrons and positrons, which are still of high energy, okay? The boost factor of this object is what? For a proton of 10 to 19 electron volt, what's the boost factor? It's 10 to the 10. So roughly the same boost factor for the electrons, 10 to the 10 times MeV, 10 to 15, 16 electron volt electrons. These are very energetic electrons. What will happen to them? I just erased it. What will happen to these electrons? Right, they will lose energy through the processes I was mentioning, inverse Compton and synchrotron if there is a magnetic field strong enough to make it pertinent. The photons emitted typically will be above threshold for making pair creation. We talked about that yesterday. An electromagnetic cascade develops. Eventually, this will contribute to the diffuse gamma ray that Kota presented yesterday as an important tool to constrain models of ultra-energy cosmic rays or neutrinos. So these are not useless. Although they carry a small fraction of the ultra-energy cosmic rays, still. Next step. There are other processes which are more important. The first process which is more important is P-gamma collision. We can repeat the same argument. Let me see. I can erase the last part here because it's not pertinent anymore. if now a proton hits a photon of the CMB in particular, this is the most abundant diffuse background, subleading level, but at lower energies, the EBL, the extragalactic background light. You may have the process P plus gamma going into P plus pi 0, or neutron plus pi plus, or multi-pion production in principle, okay? Again, you can estimate the threshold for this process to take place, exactly the same equation that I wrote before, and the result you would get is that the E proton must be larger than 2m proton m pion plus m pion square over epsilon gamma. And this is 4 times 10 to 19 electron volt. Okay? Now, from the same argument I gave before, this process is characterized by an inelasticity, which is larger. It's of the order of m pion over m proton at the threshold, which is roughly 15% or so. Actually, it's even a bit larger than that. So differently from the other one, once this happens, the proton loses a significant fraction of its energy. And basically, how likely this is to happen, this depends on the cross-section for this process. This process, close to the threshold, is dominated by a resonance state, the delta resonance, the delta baryon, which decays into this final state product. So if you look at the cross-section as a function of the energy of the photon in the frame where the proton is at rest, this has been measured, of course, in the lab. This goes from 0 to a peak, and then there are some bumps and a plateau at the end. And this peak is below, a little bit below 0.1 millibarn. This is of the order of, I think, 600, 700 microbarn. So you see, despite the fact that this is an electromagnetic interaction, it can become quite sizable, and in particular has a significant inelasticity. Okay? Once this is operational, with this information, actually, you can estimate also what's the range, the typical distance over which this particle interacts, and you will end up with an estimate which is typically of the order of tens of megaparsec. So this is the process that is responsible for making the transparency of the universe to ultra-energy cosmic rays drop dramatically at very high energies. So if we were to plot a sort of range for the range of the particle versus energy, this range is relatively large, is of the order of the Hubble distance at low energies because the only cooling is this adiabatic thing. Then there is a small drop because of the pair production, the Bethe-Heitler process, and then this drops dramatically from gigaparsec distances to maybe this is 10 megaparsec, and this is, I don't know, 4 gigaparsec. Once you are above the threshold for gamma p into pion p. Okay? If you are at sufficiently high energies, of course, this process will eventually affect also nuclei. Because in principle, a gamma can excite one of the nucleons inside the nucleus to a delta resonance and produce pions. However, for nuclei, there is a more important process that enters before this one, which is the photodisintegration. Okay? So you might have a process in which your nucleus hits a photon. Again, can be CMB or can be even the extragalactic background light photons, which are more rare but more energetic. and your nucleus loses one nucleon, or more, in principle, okay? So this is the process where gamma plus my nucleus A goes, for instance, in A minus 1 plus a nucleon plus, okay, the photon can be remitted. It doesn't matter, okay? What's the typical threshold for this process? Actually, there is a trick to do it without repeating the calculation. I told you that what are the typical binding energies of nucleons in a nucleus? Few MeV, right? 4, 5, 8, something like that. These are the typical values. What's the typical scale for this process to be open? This is the energy that you need. And this process is associated to 1 MeV. You take 1 MeV, you multiply times a factor of 4, 5, you get 10 to the 19 electron volt. So that process is roughly operational around energies of give or take factor of 2, 10 to 19, maybe 2 times 10 to 19 electron volt. Of course, it will depend on the nucleus, because not all nuclei have the same binding energies. Not all disintegration have the same binding energies, but roughly within a factor of 2 or so, they are the same. And this is the reason why Pasquale said, by coincidence, this scale and the scale I wrote there are roughly the same, but it's a coincidence, right? Okay. A final thing I wanted to mention is, of course, okay, these two are very important because just like the electron positrons, this one will disintegrate into gammas, and this will be responsible for a gamma reflux, which might be eventually absorbed by the CMB, pair production, cascades, etc., etc. This one will decay weakly into neutrino muon, and eventually the muon might decay, will decay into neutrinos, electrons, or positrons according to the sign. And this is the main culprit of the neutrino flux generation in basically all bottom-up models, unless you invoke some dark matter or whatnot. Okay? I'm simplifying a little bit. Of course, this is not the only process. There will be multiple pion production. If the energy is high enough, you might have kaon production and other things. But roughly speaking, that's by far the leading process responsible for neutrinos. Of course, in the galaxy, you have a similar process coming from a purely hadronic interaction without the intervention of photons, which is simply proton-proton, can be pp by 0 and by plus, etc. Why? Because now there is enough target for those to take place, and that's why Kota mentioned yesterday these star-burst galaxies. If you have lots of cosmic rays and you have lots of target, then this might become a very competitive process in producing charged neutrinos, charged pions, and thus neutrinos. Okay, you can compute the threshold for this process to take place. By now you should be familiar with this trick, and at the end you need not much actually. Twice m pion plus m pion square over 2 mass of the proton, which is not more than, something like 1.2 GeV. So for all practical purposes, this is an energy that all cosmic rays, which we call cosmic rays in the galaxy, have. So this is almost a process without threshold for mildly relativistic particles. Okay? So in the galaxy, there is no problem. This will take place. It's just that the rate is not humongous because the target density is not very, very large. Okay? So far, so good. I have still some time. So let's do in a little bit more detail the calculation of the secondary particles associated to the decay of this objects, of these pions. These are very simple considerations, but it's good to see them spelled out once in lifetime. By the way, you see that in these processes, there is a roughly comparable, since these cross-sections are comparable, there is a roughly comparable amount of pi 0 and pi plus. It's not exact, but roughly. So this is the origin of this strong link that Cosa was exploiting yesterday between the hadronic gamma rays, at least, and neutrino sources. Okay? Roughly, from a calorimetric point of view, the amount of energy that these processes dump into the neutrino sector and in the photon sector and eventually the electromagnetic sector are comparable. Okay? So if you remember these plots where there was some E squared dn over dE or whatever, and he was saying, okay, these are three curves that are comparable. These might point to some analogous source for these things, okay? I don't do the exact calculation of the conversion. I think there was a poster where this was explicitly reported, so you can check. Okay, so pi 0. Pi 0 decays into gamma gamma. By far, this is the dominant process, more than 99% of the time. And in the frame of the pi 0, of course, you must conserve, as usual, energy and momentum, which means that in the frame of this guy, the two photons are emitted back to back. And each photon carries an energy E0, which is nothing but m pi 0 alpha. Okay? And for those of you who are wondering what's this thing, it's 65.7 MeV. Now, what happens in the frame where the pion is moving at some speed beta? Well, of course, the energy of the let's do directly the energy of the photon. The energy of the photon will be gamma times this E0 times 1, okay, it will be plus beta cosinus theta, which means that there will be a maximum and minimum energy of the photon, E plus minus, which is nothing but gamma E0, 1 plus or minus beta. So far, so good, quite simple. In the ultra-relativistic limit, when this is moving ultra-relativistically, which is always basically the case for those processes, the mass of this guy is 100 MeV. We are talking about much, much higher energies. So this is 1. So this goes from 0 to the energy of the pion, because this is 2, the maximum value. 2 times half of the mass of the pion. Mass of the pion times gamma is the energy of the pion. Okay? So basically, the energy of the byproducts are spread out from 0 to the initial energy of the pion. How? Well, immediately from here, you see that there is a direct link, a proportionality, a linear relation between the energy of the photon and the angle of emission. Okay? So dE of the photon is E0 times gamma beta d cosinus theta. Okay? Now, the pion is a scalar particle, so this decay is isotropic, so dn over d omega is simply 1 over 4 pi. The angular dependence of the products is isotropic in the frame, in the rest frame of your particle, which is equivalent to say that dn over d, well, let's write it this way. dn is just 1/2 of d cosinus theta. This is just normalization. I'm making explicit the double differential, and I'm integrated with respect to azimuthal angle. Fine. Now I replace this. I know what d cosine theta is. So I know what is the spectrum of the photons in my lab frame. This is going to be 1 of m pion gamma beta. Why? Because there is a factor 2 that goes away with the fact that there is a factor 2 here. This is nothing but 1 over E times E of the pion times beta, which I can also rewrite as 1 over square root of energy of the pion square minus mass of the pion square. Because this is E times V, this is momentum. And momentum is the square root of energy minus the mass. We discover that the energy distribution of these things, the photons, in our frame is a box, is flat, between 0 and the maximum energy, which is the pion energy. Quite simple, huh? So this is valid in general. Huh? You have a scalar particle, decaying two-body. This is a monochromatic spectrum. In a boost frame, this will become a box. I think some of you have seen this before, but if not, this is a very generic thing. By the way, in log space, if we calculate, you have a question? No. If you calculate the average energy between the maximum energy and the minimum energy of the photon, this is irrelevant for this discussion, so let's remove it. This is equivalent to the log of square root of E plus E minus. This is not a pair electron positive. Huh? This is the maximum minimum energy of the photons. Square root comes from factor 1/2. Okay, so this is the geometric mean of the two. You do the product. This is log m pion half. There is a square root of what? Of gamma square. And then there is a 1 plus beta for the max, 1 minus beta for the mean, 1 minus beta square. Huh? This is 1 over this. There is a piece of magic, and this is just the log of m pion half. So your spectrum, look, there is no more dependence on gamma, on beta here. So if you have an hadronic source of photons, the average of your spectrum will be on the half of the mass of the pion. This is a very powerful signature, in principle. Okay, good. For a given pion, you emit photons which are, in the frame of the pion, half of the mass of the pion. In a boost frame, where the pion is moving with velocity beta, or gamma factor gamma, the photons will have a spectrum going from 0, basically, to gamma times this half energy, well, twice gamma this half energy. Okay? So you can think of it like that. In energy space, a pion, this is E0, half the pion mass. Okay? So a pion moving at a certain velocity will have this thing. Another one will have, well, let's this thing. Another one will have this spectrum, etc., etc. Now, for a distribution of pions with different energies, these boxes will have a different width. But all of them are centered around the same piece. So no matter what I do, the spectrum will present this maximum, this central point, which is half of the pion mass. Okay? This is known as pion bump. if you ever heard about it. Okay? So, of course, this is a tricky thing to measure because you need to go to very low energies if you want to see this in real life. There are some indications that in some cases the spectra measured by Fermi and Agile in some objects are consistent with this kind of feature being present. But, okay, in principle, this is a robust signature of an hadronic mechanism, which is independent of knowing the spectrum of your proton or pion source. Okay? Sometimes nature is kind. Sometimes. But our technology is not, because it's very hard to measure. Okay, now let's mention another approximation that Kota used yesterday. Okay. We want to know, in general, how to compute the spectrum of gamma rays coming from this. So to perform this kind of geometrical exercise analytically. In general, I'm assuming for simplicity here, the approximation of fixed inelasticity and single pion production that Kota was mentioning yesterday. So in general, you can assume that the energy of the pion is a fixed fraction in elasticity K pion of the proton, the parent proton producing the pion. Okay, this is not exact. It's a good approximation for, especially for analytical estimate. And then you have a source term of photons, or in general pions. Let's write first the pion source term. The Q function that enters this right-hand side. Huh? For pions at energy E pion, this will go as the density of targets, say the hydrogen density, it's the dominant one, times the integral over the spectra of the parent protons of what? Of the flux of the protons times the differential cross-section for a proton to produce a pion. Okay? This differential cross-section under this approximation, this d sigma over d EP of EP E pion, I'm writing approximately as the total cross-section for PP to produce some pion as a function of energy of the proton times a delta. Delta of what? Of the energy of the pion to be the inelasticity times the energy of the proton. Okay? If I do that, this I write delta E pion minus kappa pion E proton, and then you have the sigma PP in pion of E of the proton. Then you can integrate this, and you get the density over, in general, the inelasticity times the cross-section PP evaluated at an energy which is E pi over the inelasticity. This is roughly 20% or so. So this is a larger energy than the energy of the pion, times the flux of protons at E pion over K pion. Okay? Now, this cross-section, you can look in a particle data group. Basically, I can tell you that once you are above threshold, okay, this cross-section behaves like that. Something like a very low logarithmic growth with energy. So basically, over not so many decades, this is constant, provided that you are sufficiently far above the threshold, of course. Okay? Otherwise, if you are close to the threshold, you remember the plot Kota showed, there will be some cutoff at low energy just because you don't have enough protons on target above the threshold for producing the pions. Okay? If you are sufficiently far away, this is roughly flat. And then there is this factor here, this flux factor. If this is a power law with an index minus alpha, you see that there is an index minus alpha also for the pions. So the pions will have the same spectral index of the parent protons and the photons as well, as you can imagine. But let's show it explicitly. what's the photon source term here? Q of the photon, of the energy of the photon. There is a factor 2 because each pion produces 2 photons, of the integral up to, in principle, infinite energy of what? Of what I would call E min of E gamma, of E gamma. This is the minimum energy for a pion to produce a photon of the energy E gamma. We will compute it in a second. Of d E pion dn over d E pion. Okay? Times the source term of pions, of course, as a function of the energy of the pion. Okay? Now, let me write the result, and then I will justify this lower integration limit. M pion square over 4 E gamma to infinity d E pion times what? Q E pion, which is that one, divided by the dn, multiply this, which we derived, and this is 1 over the square root of E square pion minus M square pion. Okay? Where does this come from? Well, what is the... I told you that the energy of the photons emitted vary between a minimum and a maximum, and E gamma plus times E gamma minus is nothing but M pion square over 4, because the square root must be 1/2 M pion. And that the sum of the two, okay, the relativistic limit, plus E gamma minus is nothing but the E pion. Okay? Now we want to know what's the minimum energy for a pion to produce a photon of energy E gamma. This is equivalent to the maximum energy of a photon corresponding to a given energy of your pion. So we want to derive E plus gamma from these two expressions, and this is E pion minus E minus, and this is E pion minus M square pion over 4 E max. And if you resolve this, you will get this expression. Okay? Armed with this, now you are powerful. You can compute the gamma ray spectrum, the source term, for a given pion source term. And this allows you to compute what's the pion source term for an arbitrary flux of cosmic rays. Okay? So in principle, now you can compute the hadronic gamma ray flux corresponding to an arbitrary flux of protons. Source term. These gammas will do something afterwards. But you know the source term. Within some approximation, but for most applications, this is more than enough. Now, you can repeat exactly the same thing for neutrinos. At least for the first and most important neutrino emission associated with the pi plus or pi minus decay. Okay? You have a pi plus or pi minus that goes into mu plus or minus plus, okay, there will be a neutrino or an antineutrino of the muon type. And then this guy will eventually decay into electrons plus neutrino plus antineutrino, or, okay, I have to choose some sign, otherwise it's a mess. So for instance, mu plus, okay? This is the case for the mu plus. This goes into E plus. It goes into electron neutrino, and then you have an antineutrino, mu, okay? This is by far the most important process of the two. Why? First of all, because this is more energetic. Second, because as Kota was mentioning, there are systems where this guy will be stopped, actually, will lose energy and will decay after an energy degradation. So it may happen, in fact, that these ones are a much lower energy in the lab system. This applies, of course, for objects quite extreme, like these gamma ray bursts and other extreme objects. In the galaxy, basically, they are almost equally important, so you can almost at leading order approximate these as a four-body decay, and that's fine. Okay, I will just show the argument for this, and there is just a complication of further integral and further distribution if you want to compute the spectra associated to that. Okay, so we can repeat the same thing. What is the spectrum of this neutrino? If the muon were massless, of course, it would be half of the pion mass, just as we saw before. But the muon is not massless. Actually, its mass is a significant fraction of the mass of the pion. So in order to know the neutrino energy in the frame of the pion, we use, again, if you wish, the conservation of energy, momentum. So we write it this way. And this gives us the energy of the neutrino in the frame where the pion is at rest, which is m pion square minus m muon square over twice the muon mass. And this is roughly, well, it's roughly 30 MeV. You see that this is a bit lower than the factor 2 lower or so than the photon because of this effect. The muon is massive. Okay? Now, if the pion is moving at velocity beta, so we have to compute the energy of the neutrino in our frame. This will be given by gamma times E nu star 1 plus beta cosinus theta. Again, we can compute again the minimum and maximum value for this guy. In particular, E nu max is going to be E nu star times gamma times 1 plus beta. In the relativistic regime, this is equivalent to m pion square minus m muon square over twice the muon mass times 2 gamma. And eventually it's 1 minus m muon sur m pion square times the energy of the pion. This is sometimes also denoted simply as constant lambda times energy of the pion, and this constant is roughly 0.4 or so. Okay, you see that it's exactly the same as for the photon before. The only difference is that there is this kinematical effect of the finite mass of the muon. If we were to push the muon mass to 0, we would be back to the previous case. So this is valid in the relativistic limit, which is, again, basically always satisfied. If I work in this relativistic limit for simplicity, what do I get for the source term of the neutrino? This is going to be integral over the energy of the pion times the dn over dE for the pion times the q pion, and this is approximately in this relativistic limit given by the energy of the neutrino over lambda till infinity of dE pion of q of the pion, energy of the pion, over lambda E pion. Remember, in the previous case, there was a square root, blah, 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 which is reduced to this in the relativistic limit. It's the same thing. It's exactly the same thing. So we can go back and rederive this result still valid, okay? And we go through all the steps, and we will get to the final result, which looks exactly like this one. And there is an analogous result as this one. So even for this neutrino, you will get the result that the injection, yes, the source term for neutrinos is proportional to the flux of protons producing them. If that's a power law, the neutrino flux will be a power law as well, under the same approximation that you can neglect the energy dependence of that. Okay? There is only one step further if you want to compute these spectra, either electron positrons or these second generation neutrinos, which is that now you repeat exactly the same thing for computing the spectrum of the muon, the source term for the muon. Okay? This is just the complement of the case of the neutrino, and it will be monochromatic, so the same type of formalism applies. In the frame of the muon, at rest, then you repeat the calculation of the source term for the electron, positrons, and neutrinos, and then there is a further boost. So there is one additional integral which has to do with passing from the frame where the muon is at rest to the frame of the lab where the muon is moving. Okay? It's not very enlightening as algebra is involved. But let me mention, I think it's over the time, so let me mention a few facts of physics that are related to that. First of all, you see that eventually in this process there are also electrons and positrons emitted, respectively when there is a decay of pi minus and pi plus. Now, what happens in the extragalactic space? They follow the same fate of the Bethe-Heitler electron positrons, of course. So they will contribute to electromagnetic cascades. They will contribute to diffuse gamma rays eventually. Fine. So this must be taken into account, again, to compute in details the kind of fluxes that Kota showed you yesterday. In the galaxy, the same process happens not through photoproduction of pions, but through PP, matter production of pion. Okay? And this kind of positrons produced through PP going into pi plus and decaying into positrons are the so-called secondary positrons of cosmic rays, and they were believed to be the dominant, if not the only type of source of positrons in the cosmic ray flux. Okay? Now it turns out that this, if this is true, you can compute these quite precisely because you know the spectrum of the protons, you know the distribution of gas in the galaxy, so by similar steps, you would produce the source term of the positrons, okay? And these will reflect what? In terms of the source, the injection spectrum will reflect the spectrum of the protons that produce them. Okay? So we knew by the measurement of the protons at the Earth, essentially, we could extract the spectrum of the positrons associated to this process. Of course, they undergo transport, they undergo propagation. So there is an effect that we will discuss tomorrow that alters this spectrum, but we can compute that. Okay? So we know that if this is true, the amount of positrons, the spectrum of positrons should look in a certain way. One of the discoveries of the past 10 years is that it doesn't look at all like that. Okay? Instead of having, it has a much harder spectrum than we expected. Okay? So by now, we believe that not more than positrons up to, say, a few GeV are dominated by this process, but there must be some other process at energies above a few GeV, 5, 10 GeV or so. Probably this is what we call primary positrons. So there might be astrophysical sources or, in principle, exotic sources that inject positrons on the top of this one. Okay? Pulsar wind nebula are a quite good candidate in this sense, but there has been a lot of modeling of dark matter sources for these positrons. Okay? What else I wanted to say? I don't know if I should say anything else. No, I mentioned, of course, that there is a difference between the galactic and the extragalactic case for this. For the galactic case, this is actually true that decays at rest. In extreme sources, which are relatively dense or with very high magnetic fields, these, or sometimes even these, can cool down quite fast. And so one implication of this is that the flavor composition of the neutrinos that you get is different. Okay? If for some reason this cools down very fast, the only type of neutrinos that you produce are muon neutrinos or antineutrinos. Okay? If instead this is decaying basically unaffected, you have a ratio of E, mu, and tau neutrino, which is 1 to 2 to 0. Okay? If this is true, then, as Scott argued yesterday, after accounting for neutrino mixing, what you expect at the Earth is that they will have equal abundance of the three species. Okay? But it might not be true because, for example, of this cooling. So in principle, this is another diagnostic tool. As the plot that Kota showed yesterday, this is still at its infancy. Okay? We barely have a measurement of the flavor content of the ice cube neutrinos, but in principle, by different topologies, tracks and showers, etc., we can disentangle the flavor composition. So in principle, this is something that in the future might turn out to be another diagnostic tool to learn about the condition in the source. Okay, I stop here, and tomorrow we will do some solution of diffusion loss equation.
Yes, about these abundances, they are calculated based on the production mechanisms, or are you considering the mixing too?
Okay, this one, the top
yes.
line. Yeah, the top line is basically following from this simple argument. Okay, if this happens at rest, what I said is basically you have an equipartition of the initial energy in all the four byproducts, namely the nu mu, the electron, the nu e, and the anti-nu mu. Okay? In this limit, I'm simplifying a bit, it's not exact, but you have something which looks like one electron neutrino every two muon neutrinos summed over neutrinos and antineutrinos, I'm talking about. And through basic values of the mixing that is determined from laboratory experiment now, you can infer this ratio. It's not exact, but 10% level, that's correct. So, of course, if you have a different source, only this first step, for instance, the initial ratio would be 0, 1, 0. And what you observe at the Earth would not be anymore 1 to 1 to 1, would not be equipartition. Okay? So, or in principle, just in principle, you have another source of neutrinos at ultra energy, which has a different ratio, which is 1, 0, 0, which is actually the neutron decay. Not pion production, neutron decay. A neutron goes into a proton plus an electron plus an antineutrino. If, by absurd or by hypothesis, if this is the dominant source of cosmic neutrinos, then the ratio would be 1 to 0 to 0. And the ratio at the Earth would be modified accordingly. So there is a sort of matrix that goes from here to here that comes from the neutrino mixing formation. But this matrix is always the same. What changes is the production ratios. Okay? So, and by the way, there is an interesting aspect, which is that on Earth, typically, we are not sensitive, almost never, to these fully decohered mixing of neutrinos, because the neutrino oscillation are characterized by different baselines that depend on the on the difference of masses of squares of the masses of the neutrinos and the energy of the neutrinos. So this is a specific case that applies for astrophysical neutrinos that are traveling over very, very long distances. This is the reason, for instance, why you have quite a sizable fraction of tau neutrinos here. So in principle, this is an orthogonal test of the neutrino oscillation paradigm. Kota yesterday showed that there is even some hint in IceCube data for a component in tau neutrinos. Okay, that would be quite amazing. So I mention it because you are young. There are many other. It has been studied theoretically in the past, but now this is becoming accessible experimentally. Even new techniques to disentangle these, etc. Okay. I don't know if I answered.
So I was wondering, does the Bethe-Heitler process has anything to do with the ENCO feature of the cosmic ray spectrum?
Actually, Pasquale, and in particular his PhD advisor, have written several papers. In principle, yes. And actually, it's more than in principle in the sense that the shape of the curve that I showed you before, about that is purely determined by particle physics and the assumption that the cosmic ray flux is dominated by protons, looks extremely close to the shape of the spectrum of cosmic ray at ultra energy measured, in particular at the epoch it was IRES, I think, and then telescope array, etc. And even Auger, actually, to some extent, was compatible with that. So it was a quite beautiful theory. Protons plus particle physics, cosmologically distributed, determine the shape of what you see. Unfortunately, the data of Auger and do not seem to agree with this picture. And not only that, there are also independent arguments that apparently go against this possibility, a bit more indirect, like the fact that we have not seen any source of ultra-energy cosmic ray in the sky. So it's qualitatively in agreement with the idea that the deflections in the magnetic fields might be larger than the ones that we expect for protons. Again, this was an extremely hot topic, and the neutrinos, of course. Of course, the neutrinos are, there is a very big difference between the neutrino production in a proton-rich scenario and cosmologically evolving, etc., and a nuclear-dominated scenario. So again, this is one case where nature seemed to have tricked us into, I mean, there was a very elegant, simple explanation that unfortunately does not seem to fit the data, and unfortunately doesn't seem to be true.
Hi, so you derived the source term for the pions from proton interactions when considering that they must take a fraction lower than 20% of the proton.
Yes.
What would happen when the pions take more than that fraction? Because it's not negligible, right?
Okay. If this approximation is correct, but this number is different, it's not 20%, you just get a different rescaling here. So the formula remains valid, but the only thing that changes is that the parent proton that produces your pion is not like 5 times more energetic, is maybe 3 times more energetic. Fine. In reality, what happens is that this is not as simple. So what happens is that there is a distribution of energies, and actually there is also some multiplicity of pions, etc., etc. So in principle, you should think that at every proton, there is at some energy. It's not associated it's not associated a pion at a fixed energy, rather some distribution. Okay. Still, if you have a convolution of many protons, and at each one you associate a convolution. Sorry. Why I get always questions that force me to draw, and I'm very bad. Okay? I'm trying to convince you what happens. What happens is that even if you do this, at the end of the day, the sum of all these will look like a power law, which reflects roughly the power law of your protons. So even if I relax this approximation, qualitatively what I told you is true, unless there is a strong dependence upon energy of the multiplicity or the properties of this distribution. Okay? We don't think so because these things are measured in the lab, etc. But yes, they are, because instead, provided the Lorentz invariance is a good law, of course I can shoot, instead of shooting protons of 10 to 19 or 10 to 20 electron volts on the CMB, what I can do, I can produce a flux of gamma rays through particle physics process and shoot on protons at rest. And I study this process, right? And this is how this process was discovered, actually, in the first place, a long, long, long time ago. And I can study the distribution of energies of the pions in this. So this is not, in principle, this is known, with some errors, but this is known. They are dead. Who's the last one to decay?
So you were mentioning a lot of in a lot of decays, some particles leave and contribute to the gamma ray cascade. I was just wondering, so I imagine people have done these calculations and found that the corresponding contributions.
Yes.
How well established are they, and how does it look like for the future?
In principle, all these processes are quite well known from the particle physics point of view. So what is very, very uncertain is the relative contribution of all these channels and how the sources are distributed in redshift space, for instance. Okay, so we don't know how the sources of ultra-energy cosmic rays are distributed in redshift. Not only we don't know what they are, but also how they are distributed in redshift. And if you just change this variable, what matters the most and how the spectrum looks like would change. Okay? Plus, there are uncertainties, not on the CMB, fortunately, but on the EBL. At some subleading level, this matters. For assessing how important is the synchrotron channel in degrading the electron energy, well, we would like to know the intensity of the extragalactic magnetic fields, which we don't know. It's constrained very, very loosely. So the particle physics of it is quite under control. The astrophysics of it, not so much. Not so much. So that's what we want to use for diagnostics.
All right, I think it's a good moment to stop and thank Pasquale and Pasquale again. As well as saying goodbye to Kota, who is leaving in the afternoon. So thank you again very much, Kota, for the classes. So we convene at 3. Today is normal schedule. Go in peace. Come back.